example for the shearing stress and for the shearing strain, and we have the similar expressions. This is gamma, this is tau. So the same thing, we have G. So the strain energy density for the shearing basically equal to gamma times tau. Either way. Okay, so this turned out to be very straightforward. And so once we have the strain energy density, then for example, if an object of volume V and the total strain energy, we're using capital U. I think this, I simply follow up our textbook notation. Basically, this is the volume integral of the strain energy density dV. Okay, so that is the concept. Okay.
Wait, so really, so that's still this is still strain density or
So,
strain energy density, just
yeah.
in terms of the shearing stress and strain.
Yes,
Okay,
yeah.
just double checking.
Okay. The density that has a unit is the joule per volume, right? Or any energy like unit divided by length to the cube. Okay. And this one basically has a unit of the energy like things. Okay. So keep those things in mind. Then what we in the remaining contents we're going to see is what is the strain energy for in chapter 2 we dealing with the axial loading. And what would be the strain energy density for torsion. And also we're going to formulate what is the strain energy or strain energy density for pure bending. And the final one is transverse loading. Usually that part is a little bit complicated, so I leave it. Okay, so I leave it. If necessary, we can talk about that one. So again, with the concept in mind, and then I will introduce you the expression for each case. Okay, so basically here is the application.
So is that the volume integral of the entire shape?
Yes.
Wait, so
Not
what's
making
that?
it smaller, getting a distribution? Okay.
So always our first step is to write out the density term. And then we look up the geometry. The geometry could be any shape. Okay, then we do the integral carefully. Okay. So so the first one, the strain energy for R under axial loading. So here we assume that it's not uniform, okay, in general. consider a cross section here. So this is the actual loading with, let's say that's a P. So by taking the action reaction, we know that by taking the free body diagram on this cross section here, so here the loading is P, and say this is the area A, and furthermore, because this is not constant, uniform, so say this is position X. So for this case, A will be the function of X, and really depends on the geometry. We should be able to formulate this function explicitly. Okay, so I leave it in this way. So for this case, the normal stress sigma simply is divide P by A. Okay, and so in this way, strain energy density, if say this material has Young's modulus E, sorry. So here is 2E sigma square. Okay, so here we try to simplify is not to take up the stress and the strain simultaneously. We simply pick one. Okay, so that would be easier for us. So we plug into here, then basically here this is 2E A squared P squared. So therefore the strain energy is equal to here, sorry, let me pick up only one integral symbols, okay? Ignore the kind of bothersome. So this is a volume integral of the U dV. So that is the volume integral of 2E A squared P squared dV. Okay, so let me write it out, okay, not to confuse any, not to cause any confusion. Okay, so 3 integral symbols, that means volume integral. And sometimes you can see the dV. What is dV? So here, if I would take the small strip here, a small a plate with the thickness, so say here is dx. Okay, so basically sometimes dV can be replaced by A times dx, right? So here we might be able to, for example, if this is the with the P squared and 2EA dx, and this is a line integral from x equal to 0 to L. So for example, if the length equal to L, so from here we simply replace the dV by A dx, so we can simplify by doing the volume integral into the line integral like this one. Is that okay? So here the A dx, let me write it out here. So we cancel 1A from the numerator and denominator, so we become like this one. So this is one useful formulas for calculating for this type of problems. And usually P is a given load, and that is constant.
It just ends up being the ln, I mean not ln, but you can take out everything except for A, right? Because A is a function of x.
No, even that one could say. A here definitely is a function of x.
Mm-hmm.
If material is not homogeneous, that means material property everywhere is the same. If this material is not homogeneous, then E could be the function of x as well. So we leave E here to be more general. We can take out the E here, yeah, if E is constant. Otherwise, we leave it. Okay. So, and I think in these chapters, most of the questions we have E is constant. Okay, but here we just leave it. And so now we've done this one. The next one,